Welcome to organolysis. So this is our reaction part 4. In this video we are going to learning about some boron based reagent and some aluminium based reagent. Okay, so when we heard about some boron based reagent, the first things which is comes to our mind, that is sodium borohydride. Okay, so we also going to start from sodium borohydride. Okay, so let's see. Now see, sodium borohydride is a milder reducing agent compared to lithium aluminum hydride or any other else. Okay, so how it works? Now it generally reduces a ketone from this ketone to an alcohol. Okay, so this is how this process, and now see, the mechanism is just similar to lithium aluminum hydride. Okay, so I already made a video on lithium based reagent. You can go over here and you can check that those videos where I am discussing all the mechanism and details on lithium based reagent. The mechanism are similar to sodium borohydride also. Okay, so I am not writing over this here to overall mechanisms. Okay, now see this is a milder reducing agent compared to lithium aluminum hydride. So it has a chemoselectivity, and it has and it also a selective reagent that if a compound contains both two different types of functional groups like esters and ketone, and it selectively reduces the ketone part, not the ester part. So that is why it is very much chemoselective compared to lithium aluminum hydride. If we use lithium aluminum hydride on this compound, we get this reduced part of this and reduced part of this. And if we use, I am written here, if we use this type of compound in presence of lithium aluminum hydride, then we get this also reduced and this is also reduced, that is CH2OH. Okay, so in presence of sodium borohydride, this is not obtained. Okay, it is selectively reduced only the ketone part, not the ester part. Now let's come to the next question, that is next example, that is if you take a conjugated alpha beta unsaturated ketone like this one, and if you use sodium borohydride methanol, there is a two condition. Okay, if you use the sodium borohydride methanol, if there is no presence of cerium trichloride, that is cerium trichloride is here. If you don't use cerium trichloride, then the percentage of product that is obtained is, this one is 59%, and the both are reduced, that is double bond is also reduced and this ketone is also reduced, this is 51%. But there is one more important thing, is that if you use cerium trichloride, then the percentage of product is much shifted towards this product, that is 99% of this product is obtained and 1% less than 1% this product is obtained. That is, this reagent selectively reduces this ketone part, not this double bond or alkene. Okay, so this is very much important concepts. Okay, now this cerium trichloride in presence of sodium borohydride and methanol is selectively is called Luche reduction. I also discuss in later. Now before going to start Luche reduction, we have to know this mechanism, that is how this conjugate reduction takes place and how this product is formed. Okay, now see, this sodium borohydride is attacked conjugately to this carbon, and these bonds go here and this will go here, and then here is a negative charge, and this negative charge easily conjugate like this way. This is a resonance structure, and if in presence of ethanol, it takes a proton from ethanol and you get this ketone, cyclohexanone. So this cyclohexanone is selectively reduced by sodium borohydride, and the final workup, that is in presence of H2O plus or something else, this acidic workup, this workup takes place by this cyclohexanol. Okay, so that is how this product is obtained. But if you want to know the how selectively this product is obtained by using of cerium trichloride and 7H2, that is Luche reduction. Now see, there is a mechanism which is very much important for you. Now let's start Luche reduction. Okay, so Luche reduction is when we use Luche reduction, the main metal complex which is used, that is cerium trichloride. Okay, that is cerium 3+. Now when we use some ROH, that is a kind of methanol, or when we generally we use methanol or ethanol in presence of sodium borohydride, when we react it with sodium borohydride, try to reduce compound. Okay, now if we use this alcohol in presence of cerium trichloride, then this cerium oxygen has a lone pair of electron like this. So this lone pair of electron takes place with his and bonded with the cerium trichloride, cerium 3+ center, and then the acidity of alcohol is increased due to coordination with cerium 3+ ion. I am written over here the whole part, that is acidity of alcohol is increased just because of this oxygen is coordinately bond with the cerium trichloride center, and this is activated. This tape is just activation of alcohol. So activation of alcohol, this takes place by using this cerium 3+ ion. Okay, now see next the second step which is occurring, that is in presence of sodium borohydrate. When we use sodium borohydrate on that, now this has a hydrogen over here, so with attached to the oxygen, this borohydride's hydrogen, it's takes a proton from this activated complex, then leaves from the system in presence of hydrogen, that is H2, and then there is your negative charge over this oxygen atom, and this is obtained over here, and this negative charge is attacked on the boron center, and cerium plus ion is leaved from the system. Now see, the RO bond is attached with the boron, and that is how the second hydrogen, third hydrogen are also removed from the system by using this process, and ultimately you get this product, that is the 3 OR is OR is attacked with the boron, and the one boron hydrogen and one hydrogen is attached with the boron, and this hydrogen is used to reduce this ketone selectively. Okay, so now see, there is one important conclusion is that this is called allyl oxyborohydrates. Okay, so this is comparatively much more harder just because of this OR is this 3 OR is attached with the boron center, and that is why it selectively favors that 1,2 addition. That is selectively favors the 1,2 addition. Now this harder reagent, why we know that this center is soft center, this is soft center, and this is your hard center, just because of this is carbon attached with the carbon, but this carbon is attached with the oxygen, so it is comparatively harder than this one. So this is a 1,2 addition is occurring in this occurring by using this type of reagent. So that is why this harder reagent try to attack on the carbonyl center, that is only 1,2 addition. It follows the 1,2 addition. Now see, this oxygen has a lone pair of electron. This electron takes a proton from here, and it goes back to the oxygen over the negative charge, and this hydride which we are getting from this system, this hydride is generally attacks with this ketone, and we get the final alcohol product. Okay, that is why this we selectively reduce this one. Now see, the important step is that why we use this one with why this is attacked with this ketone. It is just because of electrophilicity of alcohol is much more increases. Okay, so that is why this oxygen lone pair is attacked with this cerium complex, and it also favors the 1,2 addition. Okay, so that is why both the systems are favorable to 1,2 addition. So that is why this product is formed. Okay, so this is very much important Luche reduction, and you have to know the mechanisms. Okay, now let's go to the examples of Luche reduction. Now see, if you take a compound like this one, there you have a alkene but a double bond over here, and the ketone also in presence of in the same compound. Then if you use the sodium borohydride and cerium trichloride, we know what will be our product. Our product is only this ketone will be reduced to the alcohol. Okay, only the ketone will be reduced to this alcohol. Okay, so this is how the product formed. Now see, if there is this is the one much more important for your exams, and you can star mark it. Okay, so if a compound that both contain a ketone also and aldehyde also, but this system, that is Luche reduction, is selectively reduce the ketone part, not the aldehyde part. And why this product is selectively, now see that the ketone is only reduced but aldehyde is remain intact. Now see why this type of product is formed. Now there is one more concept, that is, if we take aldehyde or ketone, we know the aldehyde is much more reactive. Aldehyde is much more reactive than ketone. So this aldehyde is first reacted with this methanol, and is this methanol and with aldehyde, and they form methoxyacetal, and that is this one, that is methoxyacetal. They form this aldehyde actually, okay, this aldehyde form methoxyacetal, and which is unreactive towards this Luche reduction. Okay, so that is why this aldehyde group is not reacted with this condition, but this keto group is not from this methoxyacetal, so it will react with sodium borohydride in sodium trichloride, that is Luche reduction, Luche reagent, and we get the ultimate alcohol product. Okay, so that is how the reaction, that is how this product formed. So this is one much more important concept that you have to know. Now let's move on to the next example, that is if you take this type of compounds, that is camphor type derivative, and if you take this compound, this ketone, if we want to reduce this ketone, now there is two different types of options, that is the hydride which is reacted to this system, that is there is a chance to attack over here and there is a chance to attack over here. But the important thing is that this, when we use sodium borohydride, that this attack is not possible just because of these methyl groups are interrupted, and there is some steric interaction, so this will not reacted. Okay, so that is now then this product is obtained in lesser amount. So this product when this product is much more this product is much more increases, and this is your major product, just because of this exophase is congested. That is this phase, this is called exophase, and this is your endophase. So this exophase, that is this one, so this phase is slightly congested just because of this 2-methyl group. So this product, so you get this product is in major amount, and this is your minor amount, that is 14%. But if you use the same condition of this reagent, that is sodium hydride, borohydride and ethanol, then there is also a chance to attack from here and from here, but there is no there is the exophase is not much more congested, but so that is why this product is formed in major amount, that is this is formed your 86% and this is your 14%. Okay, so there is just because of this endophase, this is your exophase, and this endophase is slightly congested, that is this one. So this phase is just closer to this one, so that is why this exophase is just slightly congested, and that is why this product is in lower amount and this is your higher amount. Now see, this is a much more important concept and much more important for your exam, and the question is also asked in CSIR June 2019. So now see, the reagent that which is used in this type of reduction reaction, that is sodium cyanoborohydride. Okay, so this cyanoborohydride I already discussed on this reagent on a previous video. You can go over here and check out those video. Okay, and how the sodium cyanoborohydride reacts. Okay, so this is comparatively much more milder reducing agent than sodium borohydride, and that is why it is much more chemoselective. Okay, it is much more chemoselective. Now this chemoselectivity occurs, that is a two types of functional group, that is ester group and a ketone group. So ketone is selectively reduced, but the ester group is intact. Okay, that you have to know. That is the chemoselectivity of this reagent. Now this type of compound has two types of phases. That is, the compound is just like this way. Okay, the compound is just like this way. That is, this compound, on this hand of this hand and this hand, these two are this cyclopentane type group. Okay, so these two bonds are there, and of this junction is your nitrogen. So this nitrogen and these cyclopentane groups are in upside, and there is this hydrogen is in upside. So now this type of complex has two types of phases, that is a concave phase and a convex phase. So in the back side, and if compound is like this, then this side is your convex phase and the upside is your concave phase. Now the concave phase is much more congested just because of these two rings are like this way, so above side is much more congested. So hydride is donated from the lower side, or you can call it convex phase. Hydride that is much more open to attack. Okay, so that is much more open to attack. So that is how this product operates. That is, the hydrogen is hydride is donated from lower side, that is from the back side, and the OH bond is moves to the upper side. So that is why this product is formed. Now let's one more important concept, that is reductive amination by using this same sodium cyanoborohydride. Now if you use aldehyde, and if you have a ketone like if you have a amine like a sodium amine like tertiary amine or secondary amine. Now this secondary amine will react to this ketone and they form this imine system. So this imine is just reduced by the sodium cyanoborohydride and they form, and the hydride is go here and this go here. This is similar is easier mechanism. So that is why this product is formed. Now let's take the example of it. Now this cyanoborohydride and this triacetyloxyborohydride is almost similar, and they almost have the same reactivity. Okay, so if you use this amine, say primary amine, to react with this ketone, you get the iminium first, and this sodium triacetyloxyborohydride will reduce this bond. So that is why that is how this product is formed. Now the let's take the next example, is that if you take this conjugated system, and there is a if now we all know how this hydrazone derivative is formed, that is in presence of a ketone. If you use a tosyl hydrogen, then you get this type of compound. Okay, so now see, sodium borohydride, when we use sodium borohydride, the hydride is donated first to this center, and this bond is open up to this nitrogen side. So when this bond is open to nitrogen has a negative charge over nitrogen got the negative charge, and this negative charge takes a proton from your acid source, that is here is acetic acid. Now this bond is go over here, and this tosyl is easily leave from the system, just because of it is very much susceptible to leave from the system, and that is why this product is formed. Now there is a hydride transfer from here, and these bonds go here, and this will leave out from the system as a here nitrogen. Okay, so now this hydrogen is migrated to this center, and this double bond is also shifted from here. Okay, now if you take a compound like this one, this sodium borohydride is this is not sodium borohydride, this hydride is converted to deuterated center. This four hydrides are replaced by 4 deuterated center. Okay, so this deuterated center first attack from this one, and this go here, and similarly this hydride, this center is there is a hydride, so this hydride is here. Now you have to know the we all know the mechanism, that is this one. Now this hydride there is a hydride of I'm written over here actually. Now see, this is how your product, and here is your deuterium. Now the similar mechanism this takes place, and the deuterium is your this side. But if you use the sodium borohydride in presence of, if you replace the deuterium in acid, okay, if you deuterate the acid system, that is here you have taken the acetic acid, but here you have taken that acetic acid's derivative of deuterated derivative. Okay, so there is a important concept that you have to know, that is there is an exchange of NH proton must be faster than reduction. Okay, that is exchange of NH proton must be faster than reduction. Okay, so that is why, and the similar processes happen, that is hydride transfer to carbon. So that is why this product is formed, that is the deuterium side is converted to here. That is just because of here you have the this NH bond is just when you have if you use ACOD, then this NH bond is now not your NH bond, that is your ND bond. So that is why this exchange of proton is much faster. So that is why this product is obtained, and here is your hydrogen. That is why this product is formed. Okay, now let's some examples of there is a use of borons that you have to know. That important examples, concept is that the use of boron. Now if you take a compound that contains both the acids, also both the acid and esters, this is your ester part and this is your acid part. So these borons, that is BH3 in presence of THF, this selectively reduce only the acid part, not the ester part. Okay, so that is also a chemoselective reagent. Okay, so that is how this product is formed. Now see, there is another example of BH3THF, that is borons of boron, is that if you take a compound like there is a here is your ketone and here is your ester, this will not reacted with ester, it's only reacted with this ketone, and that is how you get the product. Okay, now this is your important concept. Question also asks from these topics. Okay, now let's move on to our next reagent, and last reagent is that Dibal-H. Okay, so Dibal-H is there is a similarity between the Dibal-H and this reagent, hydride CO3. Okay, this is also similar to this one. Now this now see, what is Dibal-H? Dibal-H is nothing but is diisobutyl aluminum hydride. Okay, now this is the structure of this is your Dibal-H, and if you use in presence of ester or ketone, it converted to alcohol. In presence, if you use on nitriles, it will convert it to amines. If you use in epoxide, it will convert it to alcohol. So these general things that you should know. Now if you now see the mechanism how the esters are converted by using this aluminum diisobutyl hydride. Okay, Dibal-H. That this oxygen has a lone pair of electron and it will attack over this aluminum center, and this will bonded with aluminum, and this hydride is shifted towards this carbon, and this bonds goes like here. Now this has a lone pair of electron and it will attack over here, and this OR is leave from the system. Now this OR bonds the attack with the aluminum, and this will go back to the oxygen to neutralize the oxygen, and you get your final aldehyde from a ester. Okay, so this is your aldehyde from your esters. Now let's take some example. That is, if you use in presence of cyanide in Dibal-H, then also the cyanide is also converted to your corresponding aldehyde. Now this is also a chemoselective reagent, so this is also quite a milder reagent compared to lithium aluminum hydride. Okay, so there is a very good choice to use this Dibal-H. Now see, this Dibal-H is a electrophilic reagent, but we know that lithium aluminum hydride or this reagent is they are a nucleophilic reagent, but the Dibal-H is your electrophilic reagent. Okay, this is your electrophilic reagent. Now see, just because of this Dibal-H reacts slowly with electron poor compounds, and it more quickly reacted with electron rich compound. Okay, so that is why this diisobutyl lithium is a very good choice to reduce esters to aldehyde. Okay, now see here, this is your ester in presence of nitro. The both groups are converted in. If you use lithium aluminum hydride, the both groups are reduced. But when you use Dibal-H, it is selectively reduced to this ester, but not this nitro group. Okay, so that is why this reagent is quite interesting and quite useful for your converted to this esters to aldehyde. Now if you use this alkene or this esters, both are reducible, but if you use Dibal-H, then only selectively the ester is reduced to corresponding alcohol. but this double bond will remain intact. Okay, so that is how this reaction proceeds and all those things and okay, this is how this Dibal-H is reacted to this system, that is ester, nitriles, epoxides. Okay, so I hope this video is very much useful for you, and if you find this video useful, please share it with your friends. Okay, so that's it for this video. Thank you so much for watching.